And welcome to another episode of Zoom into Physics. Tonight we're going to continue the conversation around entropy, and let me start by acknowledging the traditional custodians of the land on which we are based here in Australia. And for me, it's the Teramagal and the Karamagal people of the Guringai nations, and I give my respects, pay my respect to their elders, past, present, and emerging. We had a very nice session at work 2 or 3 weeks ago during National Reconciliation Week, where one of our staff members gave a really fantastic talk about the outreach that he's been doing in Aboriginal schools around the Northern Territory and taking out physics and science and rocketry and Lego automation and all sorts of things out there, and it was really wonderful to see the science community reaching out to remote communities in Australia, and that was through the STEM Professionals in Schools initiative. So if there are any STEM professionals here that want to get involved in that, I really encourage you to looking into that scheme. It's extremely rewarding. It doesn't need to be outreach in remote areas. You can do it at local schools as well. It's something that I've done for many years, and I get a lot of joy and fulfillment out of it. So we're here to talk about entropy, and I'm joined by a prestigious panel here this evening. And I will ask that panel to introduce themselves one by one, and when they do so, answer the question: does the concept of entropy lower or raise their temperature, and why? So, Tibor, you answered that question last time, so let's kick off with you to see if your answer is the same.
Okay. No, the answer won't be the same, I'm sure. Yes, I'm Tibor Molnar. I'm an honorary associate of the philosophy department at Sydney University, and I have a particular interest in the philosophy of science and in physics in particular. So I claim to know very little physics and have very high opinions about it. So I'm the thorn in the side of all the people in the panel who actually know what they're talking about. That's my role as I see it. I don't know if I said this last month, but certainly entropy does raise my temperature. Clearly, as my entropy goes up, my temperature should go up anyway. But the more I learn about entropy, the less I understand it, the more agitated I get, because I feel like I should be understanding it. So I hope that by the end of this meeting, my entropy will be lower again, because I might have learned something.
Thank you, Tibor. And last time, Kirrily ran away because she was so afraid of the topic of entropy. I think that's why you weren't here, wasn't it, Kirrily?
Something like that. Something like that. Hi, everybody. I'm Kirrily Rule. Where do I start? So I work for the Australian Nuclear Science and Technology Organisation. I'm a neutron scatterer. I'm also the Australian Institute of Physics National Honorary Secretary. So Tibor seems to give a lot of praise to the panelists as if we all know exactly what we're talking about. But, you know, I come along to these sessions specifically so that I can learn as well. And I feel like I leave with more knowledge than what I came in for. So in that sense, I think if my knowledge is increasing, then perhaps my entropy is also increasing. So I would say that my temperature should be going up, and frankly, with the current winter weather that we're experiencing now, I'm hoping it does go up. But yes, lay it on me. I'd like to learn a little bit more. My concepts of entropy are coming a little bit from my field of research, which is looking at low dimensional and frustrated magnetic materials. So I look at things on a very quantum level. And I think that listening to last time's Zoom into Physics about entropy and having a think about how this relates to my research, I can see that size does matter. We need to think about what sort of isolated system we're talking about. So size does matter. Time does matter. Yes, and whether we're talking about an isolated system or looking at a system with everything as part of it, that does matter. So just some initial thoughts straight up there. Thanks.
Thanks, Kirrily. And lastly, I would like to welcome our special panelist guest this evening, Associate Professor Chris Ferry. Chris is Associate Professor at the University of Technology, Sydney, and the Centre for Quantum Software and Information. His research interests include quantum estimation and control, and in particular, the use of machine learning to solve statistical problems in quantum information science. If his name sounds familiar, it might be because you have a book that you read your children with titles such as Quantum Physics for Babies. And so Chris has authored, I think, as I recall, something like 50 books and along those themes, and is a wonderful author, and for which, amongst other accolades, received the AIP New South Wales Award for Outreach a couple of years ago. So please introduce yourself to us, Chris.
Oh, that's great. I'm the only one with a formal introduction, so I feel I feel pretty lucky. Yeah. So if you can see on the video, I have all the books on the shelf over there. But Kirrily held up one of them, so I'm glad that you have one. I happen to have the advanced copy of the latest book sitting next to me, so I might as well hold it up. But Scott, you said we can't swear, so I won't read the title. So that one you can't read to your kids, unfortunately. Entropy and temperature. That's a good question. So I think as an information theorist, it's something that is sort of natural to us. So I wouldn't say it lowers or raises my temperature. Maybe it raises my temperature a little bit, since we're working on the whiteboard, and that requires a little bit of energy, and so maybe the temperature increases a little bit, but not too much. So hopefully I'll be able to add something new to the discussion from the point of view of information theory.
Thank you, Chris. Well, why don't we start there, because it's a topic that we touched on just at the end of the last session, where Geraint laid the tremendous fact upon us that part of the thermal output of computers is a result of a computer forgetting information. So the example he gave is if it's computing 2 + 3 = 5, when it comes up with the answer 5 and clears the question, it's lost information, and therefore entropy it goes down, and so temperature must go up. So did anyone have any questions or comments? I think this is one that came up in, was it Chris that you were talking about that?
Yes, this was one of my 3 questions. Richard Feynman actually looked at reversible computers. So in a conventional computer, you have a logic gate like AND. You've got 2 inputs and 1 output. But in the kind of logic gates Richard Feynman was looking at in his reversible computers, the number of outputs in the logic gate is the same number as the inputs. So therefore, when it does a computation, it doesn't lose information, so you can reverse the computation and get the original inputs back. And if I remember correctly, in such a computer, in principle, I don't think it's been done in practice, but in principle, there's no heat generated. But I think there might be a caveat there. If you use that information, there might be a price to pay there, but I'm not sure about that. So maybe Chris could elaborate on that.
Yeah, I mean, I guess where I would start is to just be clear about what we mean by information, right? Because information, if you look it up on Wikipedia or in the dictionary, it probably has 50 definitions. So like we normally think of information as data, but in information theory, we have a more like strict definition. It's still a bit abstract, but what information is what resolves uncertainty. And so it's like how much could you learn by doing something, receiving a message or doing a computation. So if there's not a lot of information to acquire out there, that means you already have a lot of knowledge. And on the other hand, if you know very little, then the information content of a message or of a computer is high because you stand to learn a lot. A bit easier way to think about it is if there's a set of possibilities. So if there's a set of possibilities and there's lots of uncertainty, so it could be any one of the possibilities, then that is actually a lot of information, because by receiving a message ruling out possibilities, the number of possibilities goes down, and the amount you stand to learn also goes down. So when we talk about information, we're really talking about uncertainty. That's sort of the main thing behind it. And we try not to anyway talk about information in like its colloquial sense, which is like data stored on your hard drive, something like that. So I'll make my best attempt at sticking to that definition of information. In what you're saying, like the reversible computation, I think we can talk about the data in the computer and not refer to information. So as you said, if you have a computation takes inputs and produces outputs, and something like a traditional logic gate like AND takes 2 inputs to 1 output, and so it's not reversible. So if I take 1 and 0 and that gets mapped to 0, and all I see is 0, I don't know what inputs that came from, so it's not reversible. And that means that entropy had to be produced. So if it's reversible, then it's like a closed system in a physical sense, in which case it doesn't have to produce energy, and it doesn't have to cost any energy at all to make that computation happen. So reversible computation can be done in some sense thermodynamically for free. However, that's not how a computer works. So like an actual computer doesn't perform reversible computation. So we're not really at this level of seeing this limit. I mean, the heat generated by your computer is in performing computations. It's not in the deleting of information. But in principle, you could create a computer that performed computations reversibly, but at some point, like its memory would be full, and you would have to delete some information, and that's where the thermodynamic costs would come in.
So looking at the conventional AND gate, that exists in the universe, and the universe is a closed system. So when the AND gate does its computation, the AND gate loses information and it generates heat. Would that heat be generated because there's a loss of information there, but the information is still in the universe? So if you were to reverse the universe in time, you'll get the inputs back, if you can do that. So I'm just wondering if that loss of information with the AND gate is somehow equivalent to heat, because heat is just particles moving in these chaotic directions. So if you played a movie and played that movie in reverse, those particles will be moving in reverse, and they would somehow conspire to get this AND gate to regenerate the inputs. So I'm thinking, is the loss of information with the gate, is that information going into heat?
Chris, I think you're talking across purposes here.
Yeah.
If I understand the word universe correctly, then the universe is everything, it's all there is. And there's nothing outside it. So the universe doesn't have any inputs or outputs. The universe does everything internally. So the universe isn't an AND gate. It might have an AND gate in it somewhere, inside your laptop or something. You'd have, and it would lose heat to maybe some other component in the universe. But I don't think this operates on a universal scale, because the universe is not an AND gate, and the universe has no inputs or outputs anyway. So the entropy of the whole universe in toto is, well, first of all, unknowable. It's undefined. But secondly, I think it's not something that would vary. The entropy of the universe only goes up internally compared to something, if I understand it correctly. As a whole, it's a closed system. So whatever energy there is in the system is how much energy there is in the system. If it's not created and not destroyed, then its distribution changes. And that's why the entropy goes up, because thermodynamically it gets distributed more evenly. And so the universe suffers a heat death or something. But I don't know how, I can't quite follow how you envisage the universe being an AND gate or something. I don't know how you get inputs and outputs into the universe.
Yeah, when I say the AND gate is in the universe, I'm looking at a more at a more fundamental level. I'm looking at the AND gate as just a bunch of particles, like everything else in the universe.
Oh, okay, yeah. But then if it generates heat, then that heat will go and irritate some other particle somewhere else. There's no surprise there, I don't think.
I think
plenty of other stuff around.
Maybe part of the answer to your question, Chris, is that you know, in principle, I think this gets back to what Kirrily's point was, is like when we talk about thermodynamic systems, we really have to define what the system is we're talking about. And then you can always step back and say, oh, well, I really mean the system is something that's slightly bigger, right? So if you're thinking about an AND gate, a physical gate that takes as input signals and outputs another signal, then yeah, that's right. If you could track all of the microscopic degrees of freedom, then those degrees of freedom would have encoded on them the input. And so if you could keep track of that information, then in principle, you could reverse the AND gate, even though at the macroscopic level, it just takes two inputs to one input. But yeah, somewhere encoded in the microscopic degrees of freedom would be the input. And the reason from a macroscopic perspective that we see heat is because, well, we don't have access to those microscopic degrees of freedom. So we didn't keep track of them, so their motion is uncertain, and that's what we call heat at the macroscopic level.
Yeah.
So can we say then that the universe is the ultimate isolated system?
Yeah.
That everything else is just an approximation, and that for example, again, if I look back at the research that I do, we measure magnetocaloric effect and specific heat, and we look at what's happening with magnetism. If we apply a magnetic field, all the magnetic moments align, it saturates. We have now less microstates to consider. So have we decreased entropy? Well, in our little sample, perhaps, or at an atomic scale, maybe. But if you widen your system to look at the magnets that you've been using, the superconducting magnets, the temperature that you've been changing, no, you can't say that anymore. A lot more energy has been produced to get you to that so-called lower entropy state.
I think that's right.
Yeah, if I could just add there, so you got the universe, which, as we said, we can take as being a closed system. The universe is expanding; it's getting temperatures decreasing overall, so entropy is increasing. Okay, there's no problem there at all. Time flows, I guess you can say, forward. it's a bit of a misconception thinking that if the universe were to stop expanding sometime in the future, and then it were to start contracting, okay, entropy then would decrease, but time itself will still be the same. So you can't go saying because the universe is starting to decrease in size, that time's suddenly going to start going backwards, which some people have mentioned. But because the universe is expanding and entropy is increasing, if the universe were to start contracting, then entropy would start to decrease because it's getting to a more organized state. But the universe in itself is like, a closed room full of energy. You take energy from one spot and use it at the effect that you're taking it from somewhere else. So entropy may increase in one part of the universe, but it will decrease somewhere else. But overall, over time, entropy would have to decrease. So I think that's the general idea. You can't have entropy increasing everywhere. The net thing is entropy over time would have to increase. I can see people are thinking there.
Graham, do you know anything about gravitational entropy at all? Because that's
yes. Yeah,
okay, because that's a topic we didn't get around to last time.
Okay. Well, I mean, gravitational energy is regarded as being negative. So a lot of people think the energy of the universe is zero, where normal energy matches the gravitational energy, and the positive and negative and the zero. That is not a consensus everywhere. I mean, a lot of people think that the energy in the universe is zero, which is how the universe started in the first place, because from the uncertainty principle, the less energy something has, and the longer it can exist for, like virtual particles and stuff. So if the energy of the universe is zero, then the universe can, as a virtual system, can exist for any long period of time. If the energy of the universe was actually large at the start, then the universe couldn't exist for a very long period of time. So that's a general idea. But I think generally gravitational waves, gravitational energy is regarded as being negative. So, but you have a mass conversion. So for example, if you have two black holes circling each other, or neutron stars, to give me a gravitational energy, which means the mass of the system will decrease. So the mass of if you have two black holes, let's say 10 solar masses, and they converged, you may end up not with 20 solar masses. You may be something like 19 solar masses, because you're losing some of the energy in gravitational waves. So
maybe you misheard me. I was actually asking. That was good. I was actually asking about gravitational entropy, because I think as we were discussing just before the session, it goes in the opposite direction to thermodynamic entropy. I think if Geraint was here, he could probably talk to us about this, but in his absence, I don't know if anyone has any further information about it.
Well, as I remember it from Geraint from last time, because gravity is a negative energy, as we say, if something is highly organized, it's all clumped together, then it actually has a very high gravitational entropy, because it can't get to do any gravitational work. If something is very widely distributed, then it has a high gravitational potential energy, and you can get quite a lot of work out of it. It'll do quite a lot of work as it collapses. So a widely dispersed state, which is what thermodynamically we would say was high entropy, is in fact, as far as gravity is concerned, a low entropy state, because it will do a lot of work, and its entropy, its gravitational entropy, will increase as the system collapses and becomes highly ordered and all falls into a black hole or something. I think that's how I understand this negative entropy idea working.
So that means, Tibor, that if gravitational energy is entropy is increasing, that means in the future there's less work it's able to perform then.
Yes, gravitational work, yes.
Yes.
Now, at the same time, you might generate systems where you've got concentrations of material that will then be able to do thermodynamic work. So your thermodynamic entropy might go down, but perhaps at the same time, your gravitational entropy will go up. I don't know, have I got that right, Chris?
Which Chris?
Oh, you'll do.
I'm new Grant, am I? Yeah, so I guess I don't know what the definition of gravitational entropy is, but I mean, I'll tell you the reason why I like the information theoretic definition, because to me it just seems much simpler. So in information theory, entropy is the same as information. There's no sort of confusion about what it means and what it is, or whether it's physical, and it is just information. That's a funny story. I think maybe I'll sort of play Garant for a moment and go off on a little story tangent, which he likes to do. So in information theory, Shannon was the person who came up with this quantity, and it's a formula. So you've probably seen it before because it's the same formula as the one Boltzmann gave. And he didn't know what to call it. He thought about calling it information, but that was overused. And then he called it uncertainty. And then he met von Neumann, and von Neumann said it's the same formula as the thermodynamic one. Since nobody understands what that means, just call it entropy. And then when you use it in conversation, you'll win every argument since nobody knows what it means. and so he called it, it's now called the Shannon entropy, but it's also called uncertainty or information.
Well, and von Neumann was right.
So in information theory, entropy is just information. And I feel like that's a much simpler starting place.
So
can I? Sorry, I was going to say something.
Go ahead.
The difference is this. So let's take a simple information system like the lottery ticket. So a grid of numbers that you're going to pick a lottery. And you could pick any random set of numbers. But if you picked 1, 2, 3, 4, 5, 6, 7 out of a choice of 100 numbers, you'd think, well, that was very ordered, you know, that you would, if you went down to the lottery office, you wouldn't write 1, 2, 3, you think you'd never get that. It has to look random, okay? But in fact, of course, every combination in that lottery grid has got exactly the same kind of probability, right? So it's a simple system. The thing with physical systems is surely there is a density dependence in the probability. Just take a system where there's no electromagnetic forces and no gravitational forces, but particles are bouncing around. Now, as they get, if there's a sort of clumping in one area, the density would go higher. There'd be more bouncing and things would push apart, you see. That doesn't happen in the information system. You can have 1, 2, 3, 4, 5. Things can bunch up close, right? They can be contiguous and there's no repulsive forces. Nothing's bouncing around. But even worse, in physical systems, there's gravitational and there's electromagnetic systems. So when we say that we could have a room full of gas, and that there is a probability that all the gas could bunch up into the corner of the room. I say, no, you can't, because there's a density dependence of this, right? So as soon as it starts to bunch, all these other forces come in and make a mess of the theoretical, you know, of an ideal gas where there's, you know, which is much closer to the information one. There has to be a difference between the pure information one and the reality of gases, forces, chemical, combinations and things like that. It's nice to work with, sort of argon or something that's inert, of course. And so the more complicated the molecules are, then you're going to get all these other forces happening in the real world. Is this not true, Christopher?
No, I think what you said is true, but I wouldn't agree on ruling out like the information theoretic point of view there. And the thing is, of course, you can add all sorts of complications into the physical point of view, but you could do the same thing in the information theoretic point of view.
You could, if you were modeling it, you'd want to do that.
Yeah.
But see, it always bothered me that when von Neumann pointed to the Boltzmann equation and said, it's just like this. The Boltzmann equation was supposed to be about physical systems, but they were highly idealized, surely, right? And that when you went out and actually had to do physical kind of theoretical thermodynamic engineering, you had to then, it got a bit messy, right? Whereas when you work on a computer, it's nice and clean because, you can cut away all, you can abstract everything. And so you can have an ideal kind of situation.
Yeah, actually, I think, well, if I recall correctly, he was probably referring to Gibbs' definition, where
yes, right,
includes the distribution. So the way I see it is the physics defines the set of possibilities. So information is about all the possibilities that could happen and which ones are ruled out. Physics, the laws of physics, right? In some sense, we only have fundamental particles and the forces, and these are the rules of the game, and that enumerates all the possible states the universe could be in. One was the one where you have all the particles in the upper corner, and there's one where they're, going around and they all each have an individual position and speed. But so those are just the rules, right? The actual experienced universe is in the information that tells you which particular state the universe happens to be in. So with just the rules, actually, we don't have anything interesting, right? We need to have a way to pick which of the possible states which are valid, are consistent with the rules, is actually occurring, that we're actually experiencing. And I think that's where the information comes in. Maybe I think maybe this doesn't help because your example was I guess a bit critical of the applying like simplified explanations, but the one like first place where this connection between information and thermodynamics was observed was in this Szilard engine, right? Where you have a box and it's a gas, but it's a gas consisting of one particle, okay? And there's a piston, and it's sitting it's currently sitting in the middle of the box. So either that gas particle is on the left side or the right side, okay? If it's on the left side, then you attach a bar to the left side of the piston, and you attach a weight to it, and that particle will hit the piston and move the bar and raise the weight, and you can do work. If the particle is on the right side, you attach the bar to the right side of the piston and attach a weight to it, and the particle will hit the piston and move the piston and do work. And so it's the information about the microstate of what's going on in the box which allows you to do work. In fact, in some sense, that's all it is. If you have all the information about the microstate, then you can extract the most work out of the system, right? So if I knew that every particle in a gas like this room was in one corner, then I could extract a lot of work from that room. And if it's some other, if I define some macro state, which expresses some uncertainty about the microstate, then I can potentially do work. But the amount of work that's missing, the amount of work that I can't do, is defined by my missing information about the microstate.
Yes, I like that.
Yeah, sorry.
Chris, I think you're, oh, Peter, are you on mute now?
Yeah. How do we speak about the entropy of a single particle?
Well, so for an information theorist, the entropy is information. So that is something that that is defined for someone outside of what you call the system. So the information is what I possess about the system, which is the box that contains the single particle. And I can extract work if I know what microstate the box is in. So the particle, the particle itself as an entity is just part of the model. It doesn't have entropy.
Is that always the case? Whenever we talk about entropy, we're always talking about a system from the outside. Is that true of thermodynamic entropy too? I get the feeling that it might be.
What happens if you're interacting with the system?
Well, then it's doing work, isn't it? And you're on the receiving end of it, but you're talking about the entropy of the system. Or if you step outside yourself and look at the system as you interacting with the system, then that might also have an entropy, but that's again viewed from the outside. Again,
it's how you define your isolated system. Is it a box? Is it the room you're sitting in? Is it the universe?
Yeah, and that's something Durant conferred for me. We spoke about that in the WhatsApp. And I asked him whether entropy was a relative term, in the sense that entropy is relative to whatever it is you think the system is. And you can talk about the same devices, same contraptions in some different combination, or you include or exclude something, and it'll have a different entropy. The entropy is system dependent. It's I think it is relative in that way.
Well, that's right. And so then how do we effectively use this thing called entropy to give us information about the system, be it isolated or not isolated?
I think it gives you information relative to where you are, relative to the system you're talking about. It's not an absolute measure of anything, I don't think. It just tells you something about your situation and your relationship with some system.
I see it almost like a set of Russian dolls, you know, the small one in the middle and then the next one out and then the next one out. And the story changes, or the painting on the outside of them changes as you move further out.
Yeah, I'm inclined to share that view. Yeah, I'm not sure it's right, but I'm inclined to share the view.
Okay, so what's the relationship between entropy and information? For example, I think we agree that entropy is increasing as time goes on in the universe, but from information theory, the law of conservation of information is that's supposed to stay constant, which is what Stephen Hawking was criticized when he mentioned that stuff falling into a black hole, the information would be destroyed. And then he conceded later on that the information wouldn't be destroyed and the Hawking radiation would have information in it. So as the universe goes on, entropy increases, but what happens to the total amount of information in the universe? So from that, I would say the total amount of information would stay constant. Is that right, Chris, Ferrie? Or?
Yeah, so I think for an information theorist, I mean, we don't talk about the whole universe, right? Because that includes us, and you know, information theory is sort of a normative or operational theory. Says that try to model something to be useful for you. So I mean, if we can talk about the box again, closed box. Second law says, I mean, my favorite version is that it says that entropy never decreases in a closed system, right? So it doesn't say that it has to increase, it just says it never decreases. So that it could stay the same. And for me, that makes sense, right? So if I have a box and I don't know what's inside the box, then I can't learn anything about it without opening it. So I can't reduce the information content in the box, so the entropy can't go down. It could stay the same, but it could also increase, and it could increase if if there's, say I shake the box or I do something to the box and my uncertainty about what's happening in the box goes up. It can never go down, but it might go up. And if it goes up, that means that the set of possibilities increases, and my potential to learn or resolve uncertainty increases, and so the information in the box increases. And so I think that's sort of a hand-wavy derivation of the second law from the point of view of information. That
what about the whole universe, though, Chris? The total amount of information in the universe over time, that would stay constant. Is that correct?
Yeah, I mean, I guess I feel like when you think about the whole universe, when I think about the whole universe, I think about just a bunch of each particle just doing its own thing. It doesn't know that it's supposed to be part of a human or part of an earth or and so there's really no information at all. I mean, the information in the universe is in the particular configurations of all of the particles that are in it, and that's only useful for somebody who wants to look at it, and they carve out a part of it and say, okay, that's the system I'm interested in, and the information is just the particular configuration, the particular state that is happening inside of that box. But if we increase the box to include everything, well, there's in some information for who. Now you're imagining, you have to imagine that there's someone outside of the universe for which there could have been uncertainty for, but then you might as well just include them in the whole. So I guess it's the Russian doll thing again, right? So you have to kind of define what you mean by the system, and from I think an information theory perspective, and maybe even a thermodynamic perspective, considering the whole universe is just outside the purview of what we can give sensible answers to.
Yeah, Graham, I think the difficulty I have with your question goes back to the fact that entropy is not entropy. And by that I mean thermodynamic entropy is a different beast, different kind of animal to the information entropy. So yes, thermodynamic entropy might go up in the universe, but that says nothing at all about information entropy. That's something else entirely. And the fact that they're both called entropy, you can just have to blame von Neumann for that. So I think we're somehow talking across purposes here, and your question doesn't quite make sense, because just because one kind of entropy goes up, it doesn't mean something else, which also happens to be called entropy, but is something else. It doesn't have to go up accordingly. It doesn't have to correspond to it. I think there's no correspondence between them.
Yeah, well, that's what I thought. I mean, information shouldn't decrease over time, which is why I asked Chris, excuse me, whether there was any sort of conflict between information theory and entropy.
Well, again, you see, it's not even information. Certainly the data in the universe doesn't go up or down. There's a finite number of particles, or a quasi-infinite number or something, and they're all somewhere doing something, and there's 6n parameters in parameter space where you can define where everything is, and the amount of, if you want to call that information, that doesn't change. But that's data. I think, as Chris Ferrie was explaining, information is something else. Information is information to you about what you know about that data. It's not the raw data itself. The raw data itself isn't information. It's what you can do with it that converts it into, or that becomes information.
Sure.
And the amount of information you have does go up and down, even as the total amount of data doesn't change.
Sure. So, I mean, to me,
right?
Yeah, to me, information is data which has some sort of meaning to it. It's not just
Well,
a random set
yeah,
of numbers. So
but meaning to someone, that already is subjective. So
yeah,
it becomes subject relative. And all measures of entropy are subject relative somehow. I think.
Yeah, it's in the definition of the word information that the etymology of the word to inform means to make a form on the brain, like on the person. So that's the ancient kind of way of looking at it. So it does in the very nature of the word entail a kind of a conscious observer, an agent, and it's also possibly why. Shannon's offsider, Warren, what's his name? What was Warren's first name? He was the man who invented the word, the phrase molecular biology. Not Warwick Warren, something. In any case, Warren Weaver. He wanted to ask Shannon, because Shannon was just putting syntax down the line, and Weaver, his offsider, said, was sort of hinting, can we have meaning go down the line, right down the transmission line? And of course, he tried to do this and he couldn't get anywhere. So the only thing you could put down the line was syntax.
Yeah, that's right.
And so, but still, even when you talk about syntax of data, there is a sense that we define the frame. Okay, so when you say there's data over here, there's somebody who's drawn that line around a certain thing and said there's data there. And that's what I did it very badly last week about talking about external relations, because this is external relations between bits and pieces that are independent, which is how all this is conceived of. And there could be all sorts of different relations, and those relations give you the data or different, and so they in a sense also imply an agent who because they are attributive relations. You need to attribute the relations to make data or information. So there's always this kind of agent. So so the question to Christopher, is there an objective version of data or information?
I don't think so. No.
Okay.
I think if we go back to Tibor's point, the universe, the whole universe, right? It is in some microstate, right? And it moves from one microstate to another, and just like the lottery, each one is just as likely as another. And so from the point of view of all the particles, the particles don't care that, the second lottery number doesn't care that the one before it was 1 and the one after it was 3, right? It's just the second lottery number. So the universe is just moving from one microstate to the next. And for like an omnipotent being, entropy is always 0. It never changes. If it knows everything, then entropy is always 0. So you need to, in order to have this, like, I think the usual concept of entropy, you have to imagine a non-omnipotent being who somehow, for some reason, groups microstates into macrostates, right? And then some microstates it chooses to assign with more macrostates, and some it chooses to assign with fewer macrostates, right? So you have to imagine, like us, in looking at, say, like gases, we like partition the microstates into different macrostates. And I think that's only if you imagine that, you can say that the entropy will increase, because if you're somehow limited, then you're going to end up in a macrostate that has more microstates in it. And that means that the information in the universe also increases, because if at some point in time you get out a universe measuring machine and decide to find out what the microstate is, you stand to learn a lot more. So I think there's always an identical connection between information theoretic entropy and thermodynamic entropy from that point of view.
Is there a problem here with the language then, in that it's not the entropy of the universe or the entropy of some system which goes up and down. What goes up and down is my assessment or my attribution of entropy to that system. As you say, the system is in some microstate and it doesn't care what the entropy is. It knows nothing about nothing. What I do is I ascribe to that system something which I call entropy, and I measure it somehow. And it means something to me. So the information is actually in me, and it's my information that goes up and down. So it's almost like my entropy goes up and down, except that my entropy is about that system.
Yeah, and I think that really drives home maybe the point that Peter was getting at, that if we look at some microstate, I might assign meaning to it, and you might not, right? So that shows that data, right, or the specification is purely subjective. Like I could look at, we look at a string of symbols, of PETR, that has meaning to me, right? But to some other culture, someone who isn't familiar with traditionally English names, that's just a random bunch of symbols, right? They wouldn't call that data. They would just call that noise. So I don't think you can define an objective, an objective notion of information or data. I think it always has to be subjective.
Yeah, I think so. And that applies to entropy too, because if entropy is a measure of that information or measure of something, then that measure is as subjective as the person or the system doing the measuring.
Chris Hocking posed an interesting question before the previous session, and that was about whether a compressed computer file has more or less entropy than the raw file. And I don't know if that sort of diverts the conversation a bit, but it sounded like a really interesting question to me.
And could the physical analogy be that is, what's the entropy if you've got a little box with air in it, with a gas in it that's nicely randomly distributed, and then you just expand it, or you start with a big box and you squash it up a bit, but in both cases, okay, the pressure goes up if you put it in there, temperature goes up if you squash it, but it's still random. So what you're saying, as Chris is saying, is that the compressed file, if it's without loss, like a lossless JPEG,
So in my question, I looked at two different situations. So the first situation, in a neutron star, which is very dense, it's compressed, there's compressed matter. And this is where the Pauli exclusion principle applies. So according to this Pauli exclusion principle, you can't compress there's some kind of limit, right? It's really hard to compress it further into a black hole. I didn't like to talk about black holes because I don't understand them. That's why I'm using neutron stars. But there is kind of a limit there. And with compressed files, if you had a picture of if you had a movie, the Star Wars movie, you can't compress that down into one bit. There's got to be some kind of limit.
Yeah, sure.
So I was wondering there's a minimum limit, and I was wondering if the two were related. With the computer file, if you have a movie file, there are repeating patterns, and because there's lots of repeating patterns, that's why you can compress it down into a smaller file. So with the uncompressed file, because of those patterns, it's not random-like, but in the compressed file, because it's compressed, those repeating patterns have been removed, and so it looks random, but it's really not, because you can uncompress and get the original back. So I'm just wondering if there was some kind of link between those two examples.
There's a definition of information content that I heard, which is counted as or quantified as the smallest file you can compress something into. In other words, the minimum number of bits out of which you can re-expand the original. That is its information content. So if you have a sequence of numbers like 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on, its information content is that however long the string is, it doesn't matter. its information content is almost negligibly small. It's just a couple of bits. The information you need to store is really just start with 1 and add 1 and keep going. And you've now defined the entire string. So that's highly compressible. If you've got the digits of pi, that might be very difficult to compress. It wouldn't be very compressible. So the information content of that number is very much higher. So what you describe here with your compressibility, I think, is information content. Now, how that information content then relates to someone's assessment of the entropy of that system or state, I'm not sure. That I'm going to have to defer to a higher authority. But I think compressibility and information content are related in that way, from what I've read.
I think maybe it's related to, maybe it's the same thing as the algorithmic complexity, which is, I think, defined as the shortest computer program that could generate the sequence. And so if I have the sequence 3.14159, then that goes on for infinity, but you might recognize that as pi. And so like there's a really simple program that just says print pi. So you could compress that sequence quite a bit, but that's different than Shannon compression. So Shannon compression, I think, a simple example would be like, if I have 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, that can be compressed to just 0, 1. But both of those sequences have the same entropy. And so Shannon said, you look at the sequence, you calculate the entropy in the sequence, and that defines how much you can compress it. And I think it's the interesting thing here is that if you miscalibrate, like if you have another quantity which tells you how much compression you're losing, if you don't know the original correct distribution of what to expect when you're looking at a sequence. So if I have somebody spitting out numbers, and you assign the probability to each number, but you get those probabilities wrong, and you calculate the entropy, and you say, oh well, I can compress it by this much, you'll find that you're not achieving the optimal compression. But that's only because entropy is a subjective thing. So the person who compresses one way will see a different compression and have longer sequences than a person who compresses it another way. And I guess you can't really say one person is correct and one person isn't. It's all relative to the information that they have.
Ian, you've got your hand up, please.
Well, thank you. Yes, I was just going to say that the information content in pi seems rather paradoxical to me, because if you look at the individual digits, they go on forever. That's a very large information content and large entropy. But if you're to send another scientist, quote, PI, unquote, I think most of those scientists would be able to reproduce as much as they wanted without difficulty. Alternatively, you could send an alien the infinite series or the infinite product for pi, and that should also allow them to reproduce it all. So I think was it Tibor said earlier that the information content the term information content is only as meaningful as the ability of the receiver to understand what it's about. So that makes information content a rather weak concept compared to thermodynamic entropy, as I understand it.
Well, it's completely subjective. I mean, if you sent me the digits PI, or the characters, the alphabetic characters PI, and I had absolutely no idea what that meant, I would just look at that and say, they're two funny characters. I wonder why they're not QX. That doesn't allow me to reproduce the number 3.1415926. I can only do that if I have a whole lot of other information. So the information vests in me and not in the letters PI that communicate to me. Your PI is a token, it's a trigger that prompts me to do a whole lot of work and reproduce a number. But you're not passing the information about that number to me, because I already have to have the information about what that number is, and I reproduce it It's I don't reproduce it from what you send me. So you're only passing a token. You're not actually passing information about the value of the number pi.
And what about the infinite series, for example, which would define it to an alien, would be able to reproduce it all?
Oh, that's right. You can compress it down to some sort of infinite series. Yes.
What one is a thing, a device, and the other is a method, right? So in some ways it's more efficient to describe the thing itself, and in things that are infinite, obviously it's going to be easier to define the method of creating it if it in fact exists.
Can you not, so I think in algorithmic complexity, you have to make some assumption that like there's a computer, right? So the compression is the program that runs on the computer. And I guess you could say that the computer itself there's a program to define how to build the computer, right? So can you imagine, I suppose, there's a universal description of how to build a computer. And if that were true, then you could easily define this algorithmic complexity as the shortest program that you would stick into this particular computer to generate that sequence.
Mm-hmm.
Yeah, and even though like all the digits of pi, they look random, so it looks like it has high entropy. Of course, it you know, to one person who doesn't recognize the sequence, they might assign equal probability to each digit in that sequence, and so then they would assign that sequence high entropy. But for someone else who knows that it is the sequence of pi, then each new digit carries 0 information because they could derive it.
It's an interesting thing about pi because I've got a program here and I've calculated pi to 10 million decimal places. And it's actually quite interesting because it takes up about 97 megabytes and there's no pictures or anything in there. So what you can do, you can actually do a search of digits. So you can put your own date of birth down and then you find it's about 56 million, sorry, 1,265,000 or so digits, then that certain sequence of numbers or series of numbers comes up. So and the number of decimal places of pi is infinite, which means, you know, in any period of time you can generate anything. In fact, there is no reason why somewhere in pi it could just go 66666 continuously. There is no certainty about whether it could do that or not. So as far as being random, maybe it's not completely random.
I wonder whether there is a limit though, because I've thought that you could write, say if you wrote Hamlet, right? Shakespeare, you wrote Hamlet, and you could convert that all to just digits.
Yeah.
Where in pi could you find Hamlet, right? So without any errors, right? You see, you think, well, that's going to be, the probability of that would be, and it's just so enormously.
Right, it's small, but I mean, it's like the one about the.
That's right, but then it becomes a Cantor problem because there's infinities and there's infinities, right? And there's probably you're not going to find. So it's probably 0, right? Because then because you're going to have Hamlet with one word changed, right? And all this sort of stuff. Do you know what I mean? But you can find your birthday. That's really easy. That's as you say. But if you convert it to letters and to have a big book all laid out before you is quite impossible.
But if you have I mean, we're getting off the topic of entropy here. But if you have
not really.
If you have an infinite string, if pi is infinite, and I think we've shown that it's irrational. Then any finite string, however long, will ultimately appear in it. There'll be a non-zero probability that any string at all will appear, even if it is the length of Hamlet. It'd be valid.
No, I don't think so. I think there's a Cantor. I think it's a Cantor problem with infinities, right? There's infinities and there's infinities, right?
Yes, but here we're still only talking about one infinity, which is the length of the digits of pi. The string of Hamlet is a finite string. And there's an infinite number of finite strings in an infinite string. So there's got to be a non-zero probability of finding every single finite string you can imagine in an infinite string. It is not a zero probability. It can't be.
No,
We're talking about infinities and infinities.
I would have to agree with Tibor there. I mean, it's actually quite an interesting question that you can do the student to think that's cool and stuff. You got something like 0.999 keeps on going. And you say to the people, the students, is this approximately equal to 1 or is it exactly equal to 1? The majority of students say it's very, very close to 1, but it's not 1. But you can prove mathematically that 0.999 repeater, you know, to infinite is actually exactly equal to 1. And I think that's a similar argument. And I agree with Tibor that if you have an infinite number of numbers, then you can generate any sort of length of poetry or Hamlet or whatever on that. So,
Graham, something that would interest you that you may not know, I have actually seen a paper describing how you can calculate the nth digit of pi.
Yes, I know. Yeah,
without calculating any of the other digits.
Sure.
You
Yeah.
want to know the 1 millionth digit of pi.
Yes, you can do that.
Work out that it's a 6. The only catch is you've got to do it in binary or hexadecimal. You can't do it in decimal. But you can actually calculate a digit of pi somewhere way down the string without knowing any of the others. So it isn't random at all. There's clearly some structure to the digits. It's just not, the structure isn't evident in decimal.
A question that came up in the chat quite early on that I'd like to just cover. There was a link that Linda made to a paper at Quanta magazine entitled "Physicists Rewrite the Fundamental Law That Leads to Disorder." The second law of thermodynamics is amongst the most sacred in all of science, but has always rested on 19th century arguments about probability. New arguments trace its true source to the flows of quantum information. I don't know if anyone's been able to have a quick look at that and whether we can say anything to illuminate that for Linda, perhaps. Linda, I don't know if you're, is Linda still here? I don't know if you have a particular question about it, given that no one's probably pre-read it.
No, so the article I'm in refers to gets down into quantum theory. So I was more asking about that.
Yeah, I took a brief scan of the paper, and it looks to be telling like some very distinct stories about quantum physicists who have moved into thinking about thermodynamics, and they all I know many of them actually personally, but they all take a very, very different point of view. So if you look at this article, it's several stories that are quite disconnected, of researchers that don't have things in common. And one of the stories is actually, I wouldn't say it really has anything to do with quantum physics. It just happens to be some quantum physicists who started thinking about something different. But many of them, what they do is I guess their point of view is that the laws of thermodynamics don't have, they were built on from observations, so that they're like empirical laws. They're not derived from our most fundamental theory. So a lot of people try to come up with some derivation of these laws of thermodynamics from the fundamental laws of physics that we have, which our most fundamental laws are some form of quantum theory, whether it's quantum field theory, or maybe you probably don't even need relativistic versions. So you just need the quantum axioms, and then try to derive thermodynamics from those axioms. So there's lots of attempts at that, and then some of the other things, when the marriage of quantum mechanics and thermodynamics, are just thinking about individual quantum systems and going back to the original point of thermodynamics, which was, how do we get a steam engine to do work for us, and what are the limitations on that? So now people say, okay, say I have a few quantum systems, and I want to know, how can I get it to do work for me? And so you find out that there are new sort of restrictions that crop up because of the laws of quantum mechanics, and I mean, these are toy models that aren't at the level of something that can be tested in experiments today. So a lot of it is theoretical work about simple models like the Szilard engine, or thinking about a particle in a box sort of thing.
I think something else that comes up when we start talking about sort of the quantum level, going from a macroscopic classical idea of particles as balls down to a quantum level, is something that we haven't actually touched on tonight, and I think that we've run out of time to talk about it, is about the direction of time and time reversal symmetry. Because in quantum, we know that there is some time reversal symmetry that's preserved. So that's certainly different to what we see in sort of classical mechanics and these sorts of things. But how do you test that? That's my big question. How do we make time go backwards? Yeah, really tricky. Maybe that's a topic for the next session. Where does time play a role? Sorry, Chris.
There are some scientists like Carlos Rovelli who would say that that there's really no such thing as time. Time is something that emerges.
That's right.
I actually like that idea of that. It's becoming increasingly popular that time is a human concept, and like a chair or boat or something like that, and it's not an actual physical. Because I think Feynman actually him and a couple other physicists derived a whole lot of the equations, and what they found that the time actually dropped out of the whole thing, and they were actually amazed by it. But I mean, what Kirrily is saying about reactions and stuff, I mean, all nuclear reactions and stuff, and I guess, well, all nuclear reactions can be reversible. So, but I don't see that as being a time reversal. I see that just being the process that these things, can reverse themselves theoretically. But I don't see that as a time reversal. But as I mentioned before, the most common misconception is that the universe would have stopped expanding and would have started contracting, that time would actually reverse. That people would actually, go from an old age to a baby and into the womb or something like that. I mean, that's absolutely ridiculous. I mean, you wouldn't even notice. In fact, years ago, they didn't even know the universe was expanding. Anyway, that's probably a whole topic in itself.
Well, it worked for Dorian Gray, didn't it? Chris, to make one comment on what you said about time reversibility or time not existing, I had a very long email exchange with Carlo Rovelli, went for about 6 months, and in the end, I think we agreed to disagree. I don't think he likes me anymore because I just wasn't going to buy his story. But what I say, and the way I describe it in some of my lectures, is that I agree that we make up the concept of time. There's no doubt about that. However, in order for us to have to make it up, in order for us to need it, there's an underlying temporal extension to the physical universe. In other words, there has to be dynamics in the universe. Things change, and when something changes, it goes from being one way to being another way, and then those two ways are not at the same time. They're not simultaneously both ways at once. There is a before and an after implied by the very word event. As soon as anything happens, it divides the world into before and after. And that kind of temporal extension, that temporal extensibility, if you like, has to be innate in the physical universe. And that's why we then make up the concept of time to describe it. When we come up with an equation that doesn't have time in it, as Graham suggested, that just means we end up with a time-independent equation. Some things don't change with time. They're time-independent, like the time-independent Schrodinger equation, say. There's no time in that, but it certainly is a dynamic equation. So the temporal extension has to be there, even though time does not. And I maintain that distinction. And I don't think that even Carlo Rovelli can escape the fact that temporal extension must be a physical feature of the world, even though time itself, as the epistemic concept that we invent to describe temporal extension, that of course is of our construction. That emerges out of the physics that we do.
And Tibor, that's a perfect place to say that we are not going to have a temporal extension of this event.
Boom, boom.
We've reached time. So I think we'll call it a close there. I think we could probably do another one on these, but I think maybe we should do something different next time. For now, I'd just like to close off the recorded part of this event by just thanking everyone for another fantastic and very lively, engaged conversation about a very hairy topic, which has certainly raised my temperature about the concept of entropy even further than it was before. So thank you, everyone. Thank you, panel members, and thank you especially Chris Ferry for joining us today. Thank you very much, everyone, and have a great evening.
Thank you, Chris.
Thank you.
Thanks, everyone.
Thank
Thanks,
you.
everybody.
Bye.
Bye.
See you later.
Everyone.